Section 2.3, Part B. Show that x minus 2 and x plus 3 are factors of this polynomial. Then find the remaining factors. Well, we know that something is a factor of something else if it divides in evenly, meaning that there is no remainder. Since both of these are linear factors, I can show that they divide in evenly through synthetic division. Remember, in synthetic division, you divide by the solution that is produced by the factor. So we have 2, 7, negative 4, negative 27, negative 18, and follow through on your synthetic division process. That remainder of 0 shows now that x minus 2 is a factor. Now we have reduced it from a degree 4 polynomial here to a degree 3 polynomial here. If I synthetically divide again now by our second factor, which is x plus 3, I'm going to divide by negative 3. Go ahead and do synthetic division on that. Remainder of 0 there shows that that is also a factor. And now the polynomial that we are left with here went from degree 3 up here to degree 4 to degree 3. This is now a degree 2 polynomial, which is 2x squared plus 5x plus 3. And now we can set that equal to 0 to find the remaining factors. You could factor or use the quadratic formula. This is factorable. When we go ahead and factor this, we get 2x plus 3 and x plus 1. Set each of those factors equal to 0. Our final two solutions are negative 3/2 and negative 1. So our four solutions to this degree 4 equation are 2, negative 3, negative 3/2, and negative 1. If you were asked to find the solutions, you would be done. In this case, we were asked to find the remaining factors. Well, the remaining factors are 2x plus 3 and x plus 1. Sometimes they may ask you to take it even a step further and write the polynomial in fully factored form. This polynomial in fully factored form would be f of x equals x minus 2 times x plus 3. Those are the two factors that were given to us, times the two factors we found, which were x plus 1 and 2x plus 3. So there's that polynomial in fully factored form. Descartes' rule of signs tells us that the number of positive real zeros of a function f of x is equal to the number of sign changes in f of x or an even integer less. It also tells us the number of negative real zeros of a function is equal to the number of sign changes in f of negative x or an even integer less. Remember, when we're talking about positive or negative real zeros, that is the same thing as the intercepts when we would look at the graph of the function. So it's going to tell us how many x-intercepts there are both on the positive side and the negative side of the x-axis. So looking at this first function, find the number of positive and negative real zeros using Descartes' rule of signs. I simply count the number of sign changes from term to term. Positive to positive, no change. Positive to negative, there's one sign change. Negative to negative, that stays the same. Negative to negative, that stays the same. There was only one sign change, so that tells us the number of positive real zeros for this function has to be 1. For negative real zeros, we need to first evaluate f of negative x. When we put negative x in to this expression or this function, every place that we have x, remember the even powered terms are going to stay the same, because when I take a negative number and raise it to an even power, it becomes positive. All of our odd powered terms are going to switch. So this is going to stay as 2x to the 4th minus 7x cubed minus 4x squared plus 27x minus 18. And now in that f of negative x, we count the number of sign changes again. Positive to negative, there's one. Negative to negative stays the same. Negative to positive, there's a second sign change. And positive to negative, there's a third sign change. So our negative real zeros are going to be either 3 or 1. And that's where at the back end of both these definitions it says an even integer less. That's where that comes into play. You count the number of sign changes. You keep subtracting 2 from that until you get down to 1 or 0. Those are all of the different possibilities. So we know just from this that this function is going to cross the x-axis once on the positive side and either 3 or 1 time on the negative side. We don't know for sure until we investigate the graph more. The reason that we are subtracting that even integer is because when we get into the fundamental theorem of algebra, you're going to find that if we have complex solutions, those involving I, those have to come in pairs. Okay, so that is why we are subtracting 2 there each time. Next function, positive real zeros. Count the sign changes. There's 1. There's 2 sign changes. So positive real zeros for this function is going to be 2 or 0. Find f of negative x. We're going to get negative x cubed plus x plus 1. Count the sign changes. There's 1. There's only 1 sign change. So the number of negative real zeros is just going to be 1. That's Descartes' rule of signs. It just gives us a quick glimpse of what's going on with x-intercepts for our graph. Rational zero test. The only possible rational zeros of a function are the ratios of the factors of the constant term over factors of the lead coefficient. So all of our possible rational zeros, what we're going to do to find those is take all the factors of the constant, remember that's the number all by itself in our function, and divide by all the possible factors of the lead coefficient of our function. That list then will give us all of the possible rational zeros of our function. Remember, rational just means can be written as a fraction. So list all the possible rational zeros, then find all of the real zeros for each function. Well, our possible rational zeros. Take all the factors of the constant term. We're considering the positive and negative. In this case, our only possible ones are plus or minus 1. Take all the factors of the lead coefficient, which are also plus or minus 1. Divide all those out. Our only possible rational zeros for this function are at 1 and negative 1. That means any other x-intercepts that I have are going to be irrational x-intercepts. Well, to go ahead and find all the rational zeros, I can plug in 0, and there's nothing that we can do to solve this equation. There's no factoring we can do. We can't use the quadratic formula because it's not a quadratic. So if we don't have anywhere else to go, we are going to go to the calculator. Put this function into the calculator. Y equals x cubed minus x plus 1. Let's look at the graph. Change my viewing window here back to our standard window by hitting zoom in 6. Okay, we can see in this function, cubic, we know falls left and rises right when it's positive. We also can see that there is only one x-intercept here. Okay, we know by looking at our function here that there is a total of 3 solutions. Of those 3 solutions, only one of them is real, because when we look at our calculator, we only see one x-intercept, which means the other 2 zeros are going to be imaginary. We're only focused on real zeros right now. We can calculate that 0 by going second function trace to get into our calculate menu. Select number 2 for calculating the 0. Go to the left of where that 0 occurs. Go to the right of where that 0 occurs. Hit enter. We don't need to guess, so hit enter a third time. There's that 0 at negative 1.324718. And we know that that has to be irrational because our list of the only rational zeros was 1 and negative 1, which tells us that what we just calculated there is going to be irrational, which means our only solution, real solution, I should say, to this equation is negative 1.325 if we round to 3 decimal positions. Okay, do the same thing here. List all the possible rational zeros, then find the real zeros. Start with the possible rational zeros. Possible rational zeros, I'm going to take all the factors of that. So plus or minus 1, 2, 3, and 6. There's all the factors of our constant, divided by all of our lead coefficient, which are just plus or minus 1. If I divide all those out, our total list then just becomes what's in the numerator there, plus or minus 1, 2, 3, and 6. There's our possible rational zeros. Now we want to find all of the real zeros. Again, we know that there are 4 total solutions here because it's a degree 4. We know that that's our list of only possible rational zeros. So we're again going to go to the calculator. Now, this is where you need to pay attention because this is how you must go through this process. If you do not do it this way on a quiz or a test, you are not going to get all the points. Okay? Looking at the degree of this, it is degree 4. We need to find as many solutions with our graphing calculator, show that they are solutions through synthetic division, to reduce this down to a quadratic. So we're starting at degree 4, and each time we synthetically divide it, it reduces it by 1 degree. We need to find 2 solutions with the calculator, consecutively synthetically divide by those. That will get it to a quadratic. Once we get it to a quadratic, you must find the other 2 solutions algebraically, either by factoring or using the quadratic formula. If you just go to your calculator and write down all 4 solutions from your calculator, you don't verify that they're solutions through synthetic division, you are not going to get credit for finding any of those zeros. Okay, find as many as you need to with the calculator, synthetically divide by those until you get it to a quadratic, and then you must show algebraically how you find your last 2. So let's go to the calculator and put this function in. Y equals x to the 4th minus x cubed plus x squared minus 3x minus 6. Okay, when we graph that, we don't get a real good picture here of it, but we know we at least have 2 real solutions because we can see 2 x-intercepts. So let's go ahead and find each of those first. So let's calculate a 0. Need to find each one of those. Let's find the positive one first that looks like it's passing through about 4. So we're going to arrow over. We can have an idea, even though we can't see on our graph where we're at by looking at the x value down here at the bottom. We know that that's going to be somewhere around 4. And we can see when we fluctuate here, we're still down at negative, but now all of a sudden we're up at positive. So go over here to where we're down in the negative, hit enter. Go to the right one where we're in the positive, hit enter. We don't need to guess, hit enter again. There is our first 0. And something's wrong here with the function I put in. Let's check that. There's a bunch of other stuff here at the end that I need to get rid of. Okay, let's graph that again now. Okay, that should be the picture that you got. All right, so now we can very clearly see that only 2 of these solutions are going to be real because there are 2 x-intercepts only. So let's go ahead and calculate this again. Calculate 0. Go to the left of where that 0 occurs, hit enter. Go to the right of where that 0 occurs, hit enter. We don't need to guess, so hit enter a third time. There's our first solution at -1. Go back into your calculate menu again. Calculate 0 again, and let's find the one over on the right. Hit enter on your left bound. Go to your right bound, hit enter. Enter a third time. So -1 and 2 are the 2 solutions we are going to get from the calculator. Now we need to show that those are solutions by synthetically dividing by each one of them. So I'm going to divide by -1 and 2, one at a time. So we have 1, -1, 1, -3, -6. Synthetically divide. Remainder of 0 shows that -1 is indeed a solution. Now we're going to divide again, this time by 2, which was our other solution we found with the calculator. Remainder of 0 there shows that indeed 2 is also a solution. And now we have it down to a quadratic, x squared plus 0x plus 3 equals 0. We know from our graph that it did not appear those other 2 solutions were real because there were only 2 x-intercepts at -1 and 2. If we go and verify that here by solving this quadratic, we go to take the square root here, and we see that those last 2 solutions indeed are not real. So all of the real zeros of this function are x equals -1 and 2. Last one, do the same thing. List all the possible rational zeros, then find all the zeros. Possible rational zeros, take all the factors of the constant, 1 and 3. Divide by all the factors of the lead coefficient, 1 and 2. Now, all of these are possibilities when we take and divide all these out. So I have plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 3 over 1, and plus or minus 3 over 2. Those are the possible rational zeros. Looking at this function again, it is degree 3. So we know there are 2 or 3 total solutions to this function. Of those, we don't know how many are real, but we do know that we have to go to the calculator, and how many do we need to find with the calculator? Our goal, remember, is to synthetically divide to get it to a quadratic. Then we must show algebraically how we find the last 2. So in this case, we only need to find 1 with the calculator. That's going to get us down to a quadratic equation. So let's go ahead and put this function in. Y equals 2x cubed plus 3x squared minus 8x plus 3. Okay, when we look at this graph, we can see that it looks like all 3 solutions in this case are real. I'm going to spread this out a little bit here in my viewing window just so you can see it a little bit better. Now we can clearly see that we have 3 x-intercepts. We need to find one of them with the calculator, the other two algebraically. So let's go ahead and calculate one of them. Calculate 0. Does not matter which one we find. I'm going to go and find this one all the way over on the left. Hit enter on the left bound. Hit enter on the right bound. We don't need to guess. Hit enter a third time. We see that that is at -3. So now we verify that that is indeed a 0 by synthetically dividing by it. We have 2, 3, -8, and 3. Bring down the 2 and synthetically divide. Remainder of 0 shows that -3 is indeed a solution, which we knew from the calculator. And now we have it reduced to a quadratic. 2x squared minus 3x plus 1 equals 0. And we need to factor or use the quadratic formula to find the remaining solutions. This does factor. Set each of those factors equal to 0. And we get x equals 1/2 and 1. So our three real zeros for this function are -3, 1/2, and 1. A couple other things here that I want to talk about before we end this is those are the three zeros. If you were asked to list the three x-intercepts, you would list all of these ordered pairs. So the x-intercept would be -3, 0, 1/2, 0, and 1, 0. So know the difference between whether you're asked for solutions, this is solutions, these are x-intercepts, or you may be asked to write the function in fully factored form. Fully factored form, what solution produces, or what factor produces each one of these solutions? X plus 3. Solution of 1/2 is produced by 2x minus 1. Solution of 1 is produced by x minus 1. So you may be asked for any of these three forms for your answer. Make sure you understand the difference between the three. They're all very, very closely related, but if you're asked for x-intercepts and you give what's in red here, it is not going to be correct. If you're asked for fully factored form, you need to give it this solution right here, so make sure you understand the difference between the three. Last thing you need to be careful of is make sure when you are synthetically dividing up here that if you have terms that are missing that you put zeros in. Remember, if you don't put zeros in, the synthetic division is not going to come out right. And you should notice that because you're probably not going to get a remainder of 0. And you should get a remainder of 0 anytime that you are dividing by something that is a solution.